Good day everyone, I am Frederick Salimi. This e-course will be uploaded in our training workspace. If you are interested in full access of this e-course, please send us an email given in description. Have a good day and talk to you later.
A brief description about my qualification and experience. I have a master's degree in dependability, which covers safety, reliability, maintainability, and availability. I also have a BS degree in process control and instrumentation. I worked several years with engineering companies like Technip and operators like Total. I was involved in pre-project, FEED, detailed design, construction, and operation. Today we discuss about liquid drainage. This is a generic version and will be customized later. This course takes 1 day and we give you access to EPC 365 training monitor for discussions. The objective of this course is to give a practical understanding of onshore liquid drainage for oil and gas installations. In the following slides, I will show you different type of the liquid drainage, closed drain, open drain in hazardous area, in process facilities or storage, and in non-hazardous area like offices and the workshop, etc. Design principle for liquid drainage is one of them is segregation. What is this segregation means? Means the drainage system carry a large number of different effluents. Improper segregation of the drainage system is one of the main cause of accidents in the oil and gas installations. So segregation between closed drain and open drains. So closed drain shall always be segregated from open drain, so as to prevent pressure driving gas from the closed drain to come back up the plant via the open drain system. The piping net for collecting closed drain and open drain shall be independent, and the closed drain drum shall receive no effluent coming directly from open drains. The closed drain drum shall not discharge into atmosphere enclosure tanks drum receiving open drain effluents. And also segregation for open drain system between hazardous and non-hazardous area. So the risk of sending hydrocarbon gas from area categorized as hazardous to area categorized non-hazardous shall be minimized by segregation of the system draining this area. This is because the probability of ignition of flammable atmosphere will be higher in area designated as non-hazardous area. And also the piping collection open drain from hazardous area and from non-hazardous area shall be independent, no interconnection at all, even for maintenance purpose. Closed drains are fully contained drains, hard piped from the equipment to be drained through all the facilities necessary before safe disposal to the environment. The hydrocarbon process facilities operated under pressure, such as separator, column, compressor, pit traps, and manifold shall be connected to a closed drain system. And the equipment containing toxic fluids like CO2 and H2S shall be connected to a closed drain system. Open draining intentional release of fluid directly to atmosphere is not allowed because it would be hazardous to health and the environment. So the configuration of the closed drain system shall be independent closed drain system for hot oil, amine, TEG, etc. Normally the chemicals should be different from the each one has a closed drain system. Closed drain piping design All closed drain headers shall slope continuously down to the drain drum. There shall be no low points, very important in the piping. The minimum gradient of the horizontal piping should be the nominal diameter between 3 inch and 6 inch 1.25%, between 6 inch and 18 inch 0.4%, and greater than 18 inch 0.2%. Of course, it depends to the company philosophy and specification also. So the nominal diameter of header shall not be less than the 3 inches here. When determining the diameter of the piping, possible occurrence of the multi-phase flow shall be considered. Maintenance drain connections is very important, and you have, as a safety engineer, you have to check it in PNID, and that is one of the principles is no connection to open drain system when you have a toxic LNG, LPG, and NGL. For the flammable and non-toxic, for the bleeding, you can use this valve to go to the open drain system. And this one also, if there is no flammable, no toxic, it can go to the non-open drain system. So the maximum distance required, if icing is a possibility during the detail, is this distance required. It depends on the company. First block valve here, this is a gate valve, normally as close as possible to equipment, a straight light, no elbow from equipment to the last valve to open drain. Valve to open drain shall be here. This one should be blanket off with a blind flange. Valve to be used to bleed pressure before turning the spectacle blind, this one. And if a closed drain connection is from a line rather than equipment, a dedicated connection to the open drain may not be required. A spacer or a spectacle blind here, normally in open position, is necessary to ensure the positive isolation means are readily available for maintenance and inspection activities. And finally, it is assumed that all these equipments are all process equipment, including lines, are provided with adequate depressurization facilities. So design principle for open drain system is a design flow is the loading on drain system consists of, this is for open drain, is rainwater, firewater, and washdown water, effluent, and accidental spill. And the design system shall be designed for greater than the following case. We take one whichever is greater, normally firewater case, which is QF, which is firefighting water, and effluent is normally is greater than the others. But rainwater case, watch down case, accidental spillage case. So let's discuss about effluent categories in open drain. We have two types of the categories. One is hazardous, like oil and gas processing and storage. Non-hazardous, away from oil and gas processing and storage, like workshop, warehouse, offices. So between there are three types of contaminated water are considered for open drain. One is OD1, is permanently oil contaminated water. Example as drain from hydrocarbon processing equipment bonded areas. OD2 is accidentally oil contaminated water, is drained from the paved area around the hydrocarbon processing equipment. OD3, oil-free water, rainwater from clean surface and roofs. And 2, segregated underground network. Normally we provide, one is covering OD1 and OD2 for hazardous area underground pipe, and OD2 non-hazardous area under underground pipes. So, and OD3 is designed directly by underground infiltration or collecting the ditches along the roads. So here is the overall drainage open drain system. So here OD1 and OD2 hazardous area. Normally it goes to overflow diverter, then to go to API separator, and then oil collection basin. Or overflow goes to our directly to our observation basin and evacuation basins. And this is from OD2 non-hazardous, goes here. OD3 discharge to outside, and sanitary sewer is sewer holding tanks, goes to a sludge package, irrigation basin, fertilizer feed, and irrigation use. I wanted to show you different type of open drain equipment. There is ton dish and gully, which is taking from equipment drain, both, and also for catch basin. And this is for the outlets, and this is inlet with 300 millimeter, and this is the routing point. This is the manhole. Normally the manhole is a sealed inlet manhole, is like this, solid plate, and there is solid plate coming here and go from 300 millimeter distance outlet. There is a vent, and also there are the different types for the this is for the multiple entry. Normally onshore oil plant paved area is like this. This is a paved area. I will give you the maximum surface for this later. There are catch basins, and this goes to the manhole, and from different parts go to the manhole, and here it goes to the gullies, and the gullies and then goes to the manhole, or like this. And the manhole goes to another manhole for the treatment, etc. This is the way that the whole connection of open drainage system is designed in the plant. So the minimum installation drainage scheme, if you go through this, for example, here is test separation, and this goes to the closed drain drum here with a vent, and this effluent liquid that comes from here, and it goes to the seal pouch with a flame arrestor here, and this is with the mobile liquid disposal from here, and then goes to the observation basin. This is API separator. So this is the whole, as I said, it works like this. So to a little bit basis of number of gullies. Here the gullies, it should be the flow accommodated by one gully or catch basin should not exceed 120 cubic meter per hour. That's the sizing of this. The number of this is based on the number of flow rate that we have. I will show you later how many gullies we need for this area. And also one point about the location of the gullies. For example, here for the non-toxic services, if it is non-toxic services, gully will be located within the bounded area far from the bleed valve located in opposite side of the defined pollution sources. So here is the gullies, and if you see, it should be here. This is for the pig launcher receivers. This is the door, and indeed this is the place of gully, but this area and this valve, it is far from this area. And this for the toxic service, this gully will be located in the corner of bounded area far from the liquid, the blind flange of the defined pollution source used for cleaning. So these are for cleaning. They will be far from the gullies. Now I show you a open drainage system for an installation. And if you see here, all of, for example, this area is with the deluge here also. And there are certain areas, for example, here is only hydrants, and there are monitors, and all of these things affect the number of gullies, and we discuss about it later. So this was the fire zone 1, and there is a separation unit and MRU unit. We have a deluge system here, which the equipment will be deluge in MRU and here. And there is a monitors, there are hydrant here, and these are the criteria for the design of underground drainage. A slope of catchment area 1% minimum, maximum 4%, and 120 cubic meter per hour per gully or catch basin. And also hazardous area for catchment area is 250 square meter, 400 for non-hazardous area. The distance of travel to catch basin maximum 20 meter, and catch basin to manhole 15 meter maximum, and manhole to manhole is 70 meter. So now I show you how this is in MRU unit. MRU unit was protected by the deluge. It required 56 cubic meter per hour. There is an hydrant and there is one monitors working in this area, and as a whole we have 236 cubic meter per the 236 cubic meter per hour. We have the required the flow rate and the catch basin, because each catch basin should maximum 120. You divide this by 120, we have 2 catch basin here. And also here, this area, there is 1 monitor and 1 hydrant, which is about 200, and based on that 2 gullies were decided to put it here. So all of these things with the slope goes to the catch basin, and catch basin to manhole, and manhole to manhole. So this is the way that the system works. The same things now is for the separation area. This is a slug catcher, and this is LP separator. So the 193 cubic meter per hour for the deluge, 60 cubic meter per hour hydrant, and 120 cubic meter monitor. Total is 373 divided by 120. 4 catch basin is defined in this area, and with a slope and with the criteria that, as I said, the minimum maximum distance from catch basin to the source of the release, and the catch basin to manhole, and this was the design of the installation. Now I discuss about EPC training workspace. You go to safety engineering training and click on S12. And when you are in S12, you are in drainage philosophy. For the customized training, both onshore or offshore, company can put all the documentation here. We create an e-course like this, customized. And when it is customized, we put it for discussion and approved by company. We approve it for discussion, and we give 1 year access for discussion in different subjects in drainage system. I added a presentation by a vendor. Is Ultra Spin Technology. The address in YouTube is this, which explain about the certification guarantee for 5 milligram per liter according to EN 858. Thank you for your attention. If you have any question, please send us an email to pmc at epc365.com. We have two websites. One is in French, one is in English. There are request forms there. You can send us an email. As soon as we have it, we get back to you as soon as possible. Have a good day and talk to you in our next workshop.
Hi, welcome to the UltraSpin video series. In this episode, we're going to examine oil separators that guarantee a concentration limit of 5 milligrams per litre. We have been contacted by a number of people who ask us why they are not meeting their discharge limits with a separator certified to 5 milligrams per litre. Some separators can be certified using the European standard, but it is important to realise that this standard is not applicable to all situations. The European standard produces oily water that looks like this, which is typical of oil spills and some fuel farms. If your oily water does look like this, then a separator certified to the European standard should be able to achieve the stated discharge limit. But if your oily water looks more like this, which is typical of industrial applications such as workshops and wash bays, then the European standard is not going to be able to guarantee you any discharge limits, and the American standard is going to be more relevant to you. Here is Ivano, our engineering manager, to look at two typical standards, the European and the American, and examine how they work.
There are many different standards to test for the performance of oil water separators. Each one of them has a variety of applications. They can range from the very simple, where you're testing for simple oil spills, to the more complex, where you're testing for emulsified oil. One of the standards used by oil water separator vendors to test performance of their equipment is EN 858. As you can see, we've simulated that test here, and it's a fairly simple test. It involves water trickling down a pipe with oil dripping into that mixture. Water is allowed to flow via gravity into the collecting chamber, where at the same time fuel oil is also allowed to drip into the collecting chamber. This produces the oily water, which is subsequently allowed to flow into the oily water separator via gravity, where treatment takes place. When the water is treated, a sample is taken and the efficiency of the oily water separator is determined using this sample. The sample here is generated using the European standard, and as you can see, there is a fairly clean oil layer, and the water underneath is also fairly clean. And that's really representative of an oil spill rather than industrial application, where you don't have any chemicals or detergents or any mixing of the oil with water. Using the European testing method, there's not much mixing between the oil layer at the top and the water layer at the bottom. So if you were to take off the oil layer at the top, there wouldn't be any emulsified oil, so you would just be left with clean water. For most industrial applications, the ASTM series of testing methods is used. The most important difference between the American standard and the European standard is that the American standard intimately mixes the oil into the water to create an emulsified mixture. We first dose a known amount of oil into the water, where at this point here the oil gets injected. Here the oil is mixed into the water by a mixer, and the emulsified oily water is sent through to the oily water separator, where it is separated. The second sample is generated from our test rig using the ASTM testing method. And as you can see, there's a lot more emulsification, so this is a lot more representative of what you would find in most industrial oily water applications.
As you can see, there is no one-size-fits-all oily water separator certification standard, and no separator can guarantee that it will achieve 5 milligrams per litre discharge concentration just because it has received a certification. The Scottish EPA has issued a statement stating that the 5 milligrams per litre discharge concentration limits are achieved under test conditions. Therefore, it should not be expected that similar results can be achieved in the field.